Welcome to another video on number systems. In this video, we will have fractions also in our numbers, and we'll see how to convert numbers that have fractions in it. How to convert numbers with fractions from one base to another base. Okay. So far we have seen numbers in this format only, but you can have a fractional part to this number also. Okay, like 327.5 or 16.5. Okay, so if this is your number in decimal, what is the equivalent in the binary, or what is the equivalent in any other number base? That is what we are going to see, and we are going to look at both ways. Like if this is your number, for example, this is your binary number, what is the equivalent of it in decimal? It's always like this. So decimal to any base, you know the process, and any base to decimal. So this is what we know how to do, and based on this you can get from any base to any base. Okay, if this is your decimal number, and from here you start the fractional part. Okay, so you know that every position has some weightage. So, and this position has weightage of 10 to the power 0, this is 10 to the power 1, this is 10 to the power 2, this is 10 to the power 3, 10 to the power 4, 10 to the power 5. Similarly, after this point, so from where on the right side of the fractional part, okay, on the left side you have the integer part, on the right side of this dot you have the fractional part. The weightage at the fractional part is what? It is 10 to the power minus 1, 10 to the power minus 2, 10 to the power minus 3. Okay. Similarly, if you take any other, if you take, let's say, for binary number, if you take a binary number, so what are the weightages at each position? This is 2 power 0, this is 2 power 1, this is 2 power 2, 2 power 3, 2 power 4, 2 power 5, and this is 2 power minus 1, 2 power minus 2, 2 power minus 3. So in general, for any base, if you take any arbitrary number for any base b, for any base b, any number, this is your fractional. To the left of it is your fractional portion, sorry, to the right of it is your fractional portion, to the left of it is your integer portion. So the weights at every position is like this: b power 0, b power 1, b power 2, b power 3, and so on. Similarly, fractional part, the position, the weights at fractional part is like this: b power minus 1, b power minus 2, b power minus 3, and so on. So after 327, the next number after 327 is 328. But if there is a fraction part also to 327, and the number of digits after this dot is 1 only, so in how many ways can you, so if just think about, this is your number line sort of, and this is 327 and this is 328. Okay, and how many fraction, okay, look at the fraction part, number of digits in after dot is 1. In how many ways can you fill this digit? From 0 to 9. Okay, so from 327 to 328 there are 10 parts. So 327 to 328, between 327 and 328 it is divided into 10 parts. Okay, so this part is 327.0, this part is 327.1, and this part is 327.9, and this is 328. This is 328. Okay, so similarly, if you have any binary number, in a binary number system, let's say 101 is one integer. Okay, 101 is one number in a binary number system. The next number after 101 will be 110, right? 101 plus 1, 110 is the next number after 101. If you have a fractional part also, let's say just one digit in the fractional part, then how it will be in the number line? This is 101, this is 110, and in how many ways you can this place can be occupied? This place can be occupied by 0 or 1, 0 or 1. So how many? So it will be like, this is 101, you can say this is nothing but 101.1, and this is 110. Okay. What if you have two places after the dot? After dot you have two places, like for example 327, dot dash dash, and the next number is 328. Then in how many ways can you fill these two places? You can fill these two places in 100 ways. You can fill these two places in 100 ways, right? This place can take 0 to 9, this place can take anything from between 0 to 9. So in 100 ways, so between 327 and 328, I did something wrong here in the last video. This is not 327.0, this is 327.1. This is dot 1, this is dot 2. Okay, 327.8, 7, this will be dot 6, dot 5, dot 4, dot 3, dot 2. Between 327 and 328, because there are two digits after this dot, so it is divided in 100 parts. Okay, it is divided in 100 parts, and this part will be 327.99, this part will be 327.01. For binary, 101 dot, if you have two digits after this dot, okay, the next number is 110, but to get from 101 to 110, how many fractions have to be covered? Is how many parts have to be covered? For in case of binary, this can be 0 or 1, or this can be 0 or 1. So in 4 ways you can fill these two digits. Okay, how many fractional parts you have to cover to get to 110? It is going to be 101.00, 101.01, 101.10, 101.11, right? And the next number will be 110. So 4 parts. If you have 327 dot, and there are 3 positions after this, there are 3 digits in the fractional part, Then from 327 to 328, how you will get from 327 to 328? When you will get 328.000 after filling 1000 numbers. So this can take 0 to 9, this can take 0 to 9, this can take 0 to 9. Any number between, any symbol between 0 to 9, each digit can take, okay, in the fractional portion. So from 327.000, 327.001, 327.002, so on, 327.009, 327.010, and this way it will go on till 327.999. So how many numbers? How many numbers? This is total 1000 numbers. 1000 numbers. Because there are three digits in the fractional part, we have 1000 numbers. Because we have 3 digits in the fractional part, we have 1000 numbers. So that is why if you see the weight in case of any arbitrary number b, the weight how it is given, b to the power minus 3. So if it's decimal, if there are 3 digits, if it is decimal, if there are 3 digits in the fractional portion, it means that what will be b to the power minus 3? It will be 10 to the power minus 3. It means that in the fractional portion you will get 1000 different numbers in the fractional portion itself. And in the fractional portion, if you are getting 1000 numbers, after you include all of them, you will move from 327 to 328. You will move 1 unit in the integer part after covering all the fractional parts. You will move 1 unit in the integer part. In the integer part, by integer part, okay, in my head by integer part I use non-fractional part, okay. So you will move 1 unit in the integer part after covering all the fractional part. All the fractional part, and that is why you are doing it in terms of the inverse power. So if any number is given in any base, any number with fractions, any number with fractional part also given in any base, how can you convert it into decimal? By simply expanding it. Okay, by expanding it you are getting the ith value. In this case the ith value also includes all the possibilities in the fractional part also. I hope you get what I am saying. Let's take this number and see what is the decimal equivalent of it. 101.10. If this is a number given in the binary number system, what is the decimal equivalent of it? That we have to find out. So from any other base to decimal, you just expand it. By expanding you are basically getting the value of the ith value of the number. So let's expand it. So it will be 101. This is the integer part, dot 10, this is the fractional part. So how are you going to expand it? So this is going to be 1 into 2 to the power 2 plus 0 into 2 to the power 1 plus 1 into 2 to the power 0 plus 1 into 2 to the power minus 1 plus 0 into 2 to the power minus 1. So this is equal to 4 plus 0 plus 1 plus 1 by 2 plus 0. So this is nothing but 5 plus 1 by 2, which is equal to 10 plus 1 by 2, which is nothing but 11 by 2 and 5.5. So 101.10 in binary is equivalent to 5.5 in decimal. 5.5 in decimal. Similarly, let's take any other example. Like for example, let us take, okay, this is from binary to decimal. Binary to decimal. Let's take any other base to decimal. Any other base to decimal. For example, 0.25 in base 6. In base 6. What is the decimal equivalent of it? So this is equal to 0 into 6 to the power 0 plus 2 into 6 to the power minus 1 plus 5 into 6 to the power minus 1. So whatever the resultant is, that is your answer. The answer is basically 0 plus 2 by 6 plus 5 by 36, which is equal to 36. 12 plus 5, that is 17 by 36. So exact decimal you don't know. That is what it is. This is 17 by 36. Let's take one that will give you a complete answer. So let's take 0.25 in base 5 and find the decimal equivalent of it. So how you will do it? Just expand it. 0 into 5 to the power 0 plus 2 into 5 to the power minus 1 plus 5 into 5 to the power minus 2. So which is equal to this is equal to 0 plus 2 into 5 to the power minus 1, 2 by 5 plus 5 into 5 to the power minus 2, which is nothing but 5 by 25. This is equal to 25, 10 plus 5, that is 15 by 25, which is 3 by 5, and 3 by 5 is 0.6. So what is 0.25? What is 0.25 in base 5 is 0.6 in base 10. So this is what we have to understand, from decimal to base or base to decimal. So we're just going to formalize it from any other base, from any base to decimal. How you will do it? So any base is, let's say a number is like this, bn minus 1, so on, b3, b2, b1 dot, let's denote it like b minus 1. It's just for denotation, b minus 1. It can go on. It can go on. Let's take until 2 places only. If this is any arbitrary number in base b, okay, what is the decimal equivalent of it? You just have to expand it. Okay, weighted sum. The weighted sum is your decimal equivalent. Is your decimal equivalent. Weighted sum is your decimal equivalent, and that is equal to bn into b to the power n minus 1 plus bn minus 1 into b to the power n minus 2 plus so on b3 into b to the power 2 plus b2 into b to the power 1 plus b1 into b to the power 0. Okay, this will give you the integer part. This will give you the integer part. The integer part or integer equivalent. Integer equivalent in decimal. Okay. Plus b minus 1 into b to the power minus 1 plus b minus 2 into b to the power minus 2. So this is your decimal, the fractional equivalent in decimal part. This is your fraction equivalent in decimal. Fraction equivalent in decimal. Okay. Now, what about decimal to any base? So let's say this is like t n dn minus 1 dn minus 2 so on d3 d2 d1 dot d minus 1 d minus 2. Okay, this is your any typical decimal number with 2 digits in the fraction part. Okay, in the last video when fractional part was not in the picture, how you got the integer equivalent, means the number equivalent in other base for the integer part of the decimal? For this portion, what did we do? Remainders in the reverse order. Remainders in the reverse order by repeated division of first the integer number itself, first the integer part and then the quotients and then the successive quotients. So you know how it happens in the last video. If the phrasing is not accurate, then make it accurate. How to get the equivalent in the decimal portion, in the fractional part? So in this case, you will continuously multiply the fraction part with the base. So in the integer part, you are dividing it with base. Okay, repeated division of the first integer part and then successive quotient by base. By base b. By base b. Okay. By base b. So let's say this is any base b, any arbitrary base b. Repeated multiplication of the successive fractional part till you get 0 in the fractional part. Till you get 0 in the fractional part. Repeated multiplication of the successive fractional part with base b. till you get 0 in the fractional part. Okay. And what is the equivalent number? What is the equivalent number? The equivalent number is, like here, the remainders are the, with remainders you get the equivalent number. Here you have to collect the integer parts, collect all the integers in the way, collect all the integers in the way to get the equivalent fractional portion, in the way to get equivalent fractional portion. Fractional portion in base B. Okay, let's look at examples and finish it off. So let's take one example of a decimal number 37.25 in base 10. Let's take one example of a decimal number, let's say 56.25 in base 10. What is the this binary equivalent of it? Let's find out. So you know that for 56 what you will do, 56 to 28 to 14, okay, 228 remainder 0, 214 remainder 0, 27 remainder 0, 2 into 3 remainder is 1, 2 into 1 remainder is 1, 2 into 0 remainder is 1. So the 56 equivalent is reverse of this. So 1 1 1 0 0 0 base 2. And for 0.25 what are you going to do? For 0.25 what it says, repeated multiplication of the successive fractional part. So 0.25 into, what is the base? Base is 2, so 0.25 into 2, that is equal to 0.50, right? So 0.50 into 2, this is nothing but 1.00. Okay. So you get the 0 in the fractional part. You get 0 in the fractional part. So what is your fractional equivalent part in the binary? It is 0 and 1. 0 and 1. So 56.25 in base 10. 56.25 in base 10 is equivalent to 111,000.01 in base 2. Let's take one more example. This time, okay, let's take one more example from decimal to any other base, but not binary. Let's take 37.25 in base 10. And what is the equivalent of it in base 6? So how you get it? For 37, 6 into 6, remainder is 1. 6 into 1, remainder is 0. 6 into 0, remainder is 1. So for 37, what is the equivalent of 37? It is 101. So 37 in base 10, this is equivalent to 101 in base 6. What about 0.25 portion? 0.25 into 6. What you will get? You will get 1.50, right? Now what is the fractional part? 0.50 is the fractional part. So 0.50 into 6. This is 30 to 300 by 3.00. 3.00. So you get 0 in the fractional part, so you will stop here. And the integer portion is 1 and 3. So the required number 37.25 in decimal. The equivalent of it in base 6 will be 101.13. Okay, let's stop here. Thank you very much.